Hello, everyone, and welcome back. In this lecture, we're going to build upon what we've been speaking about in the previous two lectures. And again, the goal here is to find the volume of a general shape in three-dimensional space. I'll remind you that in the previous lecture, we introduced what was called the disk method. And this gave us not only a way of calculating volume, but also creating these three-dimensional shapes by revolving them around an axis. Today, we're going to speak about how we can generalize this in order to construct shapes where we're not directly revolving around an axis connected to the shape. Let me show you what I mean here. Let's imagine that I give you some general region in two-dimensional space. So let's say I give you a region that looks like this, and I ask you to revolve this thing around the x-axis. So I'm going to take it, and I'm going to revolve it around like this. Now, this isn't directly applicable to what we spoke about in the previous lecture, because if you'll look back at your notes, in the previous lecture, we were only revolving around an axis that was directly connected to our shape. In this case, there's a gap. If you picture what this shape looks like, it sort of looks like a vase without a bottom on it. And so you have this hollow inside, and then this walled off region that forms the actual shape. So the question is, how do we find the volume of this more general shape? Well, if we think about what happens when we take a cross section here, things are still circular, but basically what you would get, if you look down on this thing from above, you would see these circles with a hole punched out of the middle, so a punctured disc. And so the sectional area is given by the area of that shaded yellow region here. So the question is, how do we find that area of this thing? Well, basic geometry would tell us that we would find the area of the large circle. So that thing we'll say has radius capital R of X. And we would subtract the area of the smaller inset circle, which we call little r of x. And so what this means is that the cross-sectional area in this case is going to be pi times capital R of x squared. So that's the large circle. And then we punch out the small circle in the center, given by with radius little r of x squared. So if we factor this thing, we can take the pi out, and we're left with capital R of x squared minus little r of x squared. And that will give us the cross-sectional area that forms the washer method. And you can see why it's called the washer method, because this punctured disc resembles a washer. Now, I really, really want you to be careful when you do this, because some people try and do this. They say that the area is equal to R of x minus little r of x, and then they square all of that. But this is 100% wrong, right? The squares on each radius individually. So let's take care not to make that mistake. We have to square the radii, then we do the subtraction. And we call the capital R the outer radius, while we call the little r the inner radius. And so this tells us that the volume obtained from this revolution is given by the integral, a definite integral, from your bounds a to b again, of your cross-sectional area. So that never changed over the past 3 lectures. The only difference here now is that your cross-sectional area is this area of the washer. So there's a slight modification to this method coming from that inner radius. So let's just jump right in with some examples. Here's the first example. I'm going to ask you to consider the region that is bounded by the curve and this will be y is equal to x squared plus 1, and the line y is equal to minus x plus 3. And this thing is revolved around the x-axis to generate a solid. And so the question is to find its volume. Okay, so as we saw in the previous few videos, the way that we should be starting this is by offering up a little sketch. And we've all seen my sketches. They don't have to be that pretty, but they should be used for a visual guide for us. So let's start with the line. Oh. So this is y is equal to minus x plus 3. And then our parabola in here, so this isn't going to be drawn perfectly to scale, is given by y is equal to x squared plus 1. Let's zoom in a little bit. I think I zoomed out too far here. Okay, that should be a little easier to see. So the first question we have to ask ourselves is, what is the volume that we're actually, or what's the area that we're going to revolve? Well, that's going to be this area. So between these points of intersection, it's going to be right in here. And then what we're doing is we're taking that and we're wrapping it around the x-axis. And so the question becomes, what are these left and right extremities? And what are the inner and outer radii? So I think the second question there of the radii is easier to answer. So let's start with that. So we can see that the outer radius is going to be from the center of the object, so that's the x-axis, all the way up to the top or the upper curve. So in our case, this is going to be minus x plus 3, so up to the green curve. That means that my inner radius is going to be given by the parabola x squared plus 1. And so now we have to ask ourselves, what are the bounds or the limits on this integration? So call them A and B. We need to find these, and we can see that these can be located by finding the points of intersection between these two functions. So we've done this before. Let's go ahead. This requires us setting x squared plus 1 equal to minus x plus 3. We can rearrange this thing to give us a nice quadratic polynomial, which we are required to find the roots of. This can be factored into x plus 2 and x minus 1. And this gives us two solutions. X is equal to minus 2 and x is equal to plus 1. So that tells me that my A value is minus 2 and my B value is positive 1. Now we have all of the ingredients needed to apply our formula to find the volume of this thing, right? We have the inner and the outer radii. We have the bounds of integration. Now we just need to put everything together in order to find this volume. So let's start a new page here and let's calculate out this volume. We know that the volume is equal to the integral from -2 up to +1 of pi times the outer radius squared. So in this case, it's going to be -x plus 3 squared minus the inner radius squared, x squared plus 1 squared dx. We can expand out these square terms using say a FOIL operation. And this will give us a nice quartic polynomial. So we get 8 minus 6x minus x squared minus x to the 4 dx that we are being asked to integrate here. And so in this case, the integration yields 8x minus 3x squared minus x cubed over 3 minus x to the 5 over 5. And this is running from -2 to +1. And so now I'll leave the algebra to you. Once you plug in these upper and lower bounds, you get 117 pi over 5. Again, like most of this, it's the process that truly matters the most. The final answer, is not particularly interesting. There's no real significance for 117 over pi over 5, but getting up there and understanding this process, what the washer method really does with these inner and outer radii, that's the important concept here. So just like in the previous lecture, we saw that you don't have to use x as your integration variable all the time. You can use y as well. And so let's take a look at an example where we do that. So here's a second example for everyone. So the idea here is that, so we're given the region bounded by the parabola y equal to x squared, and the line y is equal to 2x in the first quadrant. Is revolved around the y-axis. To generate a solid. And so, of course, the question is, find its volume. Okay, so the first place that we're always going to start here is with a little sketch. Again, I am not exactly offering up an artist rendering here, but I hope you appreciate the sketch nonetheless. Let's start with the parabola. So this is y is equal to x squared. Then we have the line. This is y is equal to 2x. So we can see that the region is given by this small little region here. We are bounded by these points of intersection. Clearly, one of them is at the origin. And we are rotating ourselves around the y-axis in this case. So now we have to look at the inner and outer radii in terms of the variable y, right? Because this tells us that we have our inner radius going over to the red curve, and our outer radius going over to the, oh, sorry, those shouldn't be in X anymore. Pardon me. Those should be in Y. So now what we can see is that we have the outer radius given by the green curve and the inner radius given by the red curve. So the question is, how do we actually calculate these things? Well, the first thing that we're going to have to do is calculate the radius as a function of y. So here we're going all the way out to y is equal to x squared. In this case, y is determined by x. We want x to be able to be determined by y. And the reason for this is because the radius is moving perpendicular to the x-axis. So if we take square roots on both sides, and we use the fact that y is positive in this case, x is positive in this case, we get the square root of y. Similarly, if we rearrange y is equal to 2x, we rearrange that function as x as a function of y. This gives us y over 2. And so now the question is, what are the bounds on integration? So if we switch over here, we can see that we are clearly going from the origin, y equal to 0, up to some mystery point, which is given by the intersection of these two functions. So the question is, where do these two functions, where do they overlap? So we can do this again by solving x squared is equal to 2x. That's setting these two things equal to each other. We can solve for x, then we can get the y value, or we could use the inverse functions and solve for y and get the x value. It doesn't matter which way you want to do it. It's just more natural for me to use x. But clearly there's one solution when x is equal to 0, which we already knew. But then there's another solution when x is equal to 2. So that tells me that this point is given by 2, and then I can plug it into either of those curves to find that the corresponding y value is 4, which tells me that I'm going to be integrating from 0 up to 4. So let's do this. So this tells me that the volume is the integral from 0 to 4 of pi, and now the inner radius, or sorry, the outer radius squared, so the square root of y squared minus the inner radius, y over 2 squared. And in this case, we're integrating with respect to y. So let's factor that pi out of this, and I get a definite integral of a nice polynomial function. So y minus y squared over 4 dy. Again, this thing is polynomial. It's a relatively simple thing to integrate. So I get y squared over 2 minus y cubed over 12, all running from 0 to 4, which you can plug in those upper and lower bounds. And in this case, you get 8 over 3 pi. So again, the final answer isn't that exciting, right? There's nothing particularly special about 8 over 3 pi. But what is exciting is that now we have a new method at our disposal to not only create objects through these revolutions, but also calculate their volumes. So this is the method of washers. Okay, thank you very much for watching.